Okay, a vector valued function is going to be a function of the form r of t. So t is the independent variable, and the result when you plug in a given t is a vector. Okay, so that's the way a vector valued function will look. You can think of it in several ways. For a given t that you plug in, you're getting a vector, and you can view that vector as pointing to the point on the curve. Okay, so this is for a given t value, t equal to a, and then plug in a different t. You're going to have a range of values for t, and for each t in that interval, you're going to have a different vector that's pointing to a point. Okay, so you can look at it as parametric equations where you have x equal x of t, so it's going to be some function of t, y is y of t, z is equal to z of t. So you can think of it as parametric equations, for these given values of t, or you can think of it as the vector as a result of plugging in that value of t. Okay, so each point on the curve corresponds to a vector. So you've got a point here, there's some vector that points to it. It's kind of like it's moving along, tracking it. So here's the initial value of t, and as t increases, we're going to be over here to the last value of t. Well, the last value of t will be where the end point is. Or we let t be infinite, and then we would go on infinite in both directions. Okay. So the entire curve we represent by that. So that'll be the form that describes the whole curve. Okay, like I said, you can view each vector as, the point is the head of that vector. Okay, so this definition of a curve in space, it's going to be a vector valued function. So it's going to be of this form. And so instead of calling it x of t, y of t, h of t, they just use functions to represent those. So f of t, g of t, h of t. And so since this is a vector, you can see the brackets around it, we could also write it in the ijk format. F of t is the ith component, g of t is the jth, and h of t is the kth component. Okay, now each of the functions f, g, and h are just real, valued functions that, use t is the points in the domain. So the domain of R is just the values of t, and if you want to find the entire domain, the greatest domain is the set of all the t values, so that f, g, and h are all going to be defined, they have to exist. So you can find the domain of this function by just looking at the individual functions and seeing where they're defined. Okay, so let's find a vector function. So I want the form r of t equal f of t, g of t, h of t. So that's what I'm looking for. Now I want a line that's passing through these 2 points. So now we've seen before that if we want to find the equation of a line passing through 2 points, a line's equation has 2 forms. We can either write it as r equal r naught plus t times v, that's the vector form, or we can write it as parametric equations where you have x, y, and z equal, and we know it's x naught, y naught, z naught, plus at, bt, ct, where ABC is a vector parallel to the line. Okay, so we have 2 points, so we haven't been given the vector. So what we can do though is we can just find PQ, the vector PQ will be parallel to the line since that passes through the 2 points. So the vector PQ is just 3 minus 2 is 1, 0 minus -1, 6 minus 4 is 2. Okay, so that's what we're going to use for the vector V that's parallel to the line. And now pick either one of the points. They don't indicate a starting or ending, so we'll just pick one of them. So the parametric form of the line would be x equal 2. Going 2, -1, 4 would be the point I'm going to use. And then plus 1t, plus 1t, and plus 2t. So that's the parametric form of the line. So now they want the vector function though. So we're going to write it as r of t. The f of t, that's the x, the function of t that gives the x, so 2 plus t. Y of g of t is just the y, so it's -1 plus t. And h of t is 4 plus 2t. So if you're given a vector valued function and you see each one of the equations, the f, g, and the h, or a constant times t plus a number, you know that you've got an equation of a line. So this is just a curve in space, and it's defining the line that passes through those 2 points. Okay, so one concept that I want to talk about, we've talked about these parametric equations, and when you have t values that are, in an interval that's defining this vector valued function. So you've got an r of t okay, and so t is assumed to be all real numbers or an interval that you specify. So now if they give you an interval, you're defining an orientation for this curve. So you're going to give it a starting point and you're going to give it an ending point by those parameter values. So r of a is the beginning of the curve, and r of b would be the ending point of the curve. Okay, and so the orientation would be going from, so if you have a point r of a here, and you have some point r of b here, it's not just a curve between them, but it's defining a direction. So that's what I mean by the orientation. So the positive direction of a parameterized curve is in the direction in which the tangent vectors point along the curve. So I haven't talked about the tangent vectors. If you have a curve, you have a tangent vector at any point. In fact, at a given point, you have a tangent line. So you have 2 tangent vectors. One of them would be going from that point that direction. The other one would be going from that point in this direction. Okay, so if you've got a curve like this, you have 2 separate tangent vectors, or 1 tangent line at each point. Now, if that curve is unparameterized, meaning that there is no starting and ending that's specified, like by the interval giving the values of t like this. So if this is unparameterized, we have 2 separate tangent vectors. We have that one, tangent line and 2 separate tangent vectors. So one points in one direction, the other points in the other direction. But if we have a parameterized curve, so they've specified some sort of a interval where there's a start and an end, then there's only one tangent vector. The tangent vector that we would be referring to then would be the one that is pointing to the direction that the movement is occurring. So notice the little arrows here. These arrows are indicating the direction that is defined by the vector valued function. And so if we're moving in that direction, then the only tangent vector that we are going to worry about is the one that points in the direction of movement. So just be aware of that as we start getting into tangent vectors as well. So positive and forward direction is the direction the curve is generated as the parameter increases from A to B.